Hey there, I'm Nix, and the topic of today's video is the implement strStr problem on the LeetCode website. As always, solving this problem in the C++ language and giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of the time and space complexities of the algorithm, as well as looking at LeetCode rankings. If that sounds good to you, then stay tuned. Welcome back, and let's get started. So, as the problem title suggests, for the implement strStr problem, we want to implement strStr. Now, if you click on this, it will send you to c++.com, which is a nice reference website for learning all about various methods and all about C++. But let's get rid of that. And essentially, we want to return the first index of needle in haystack, where it's located, or if we can't locate it and it's not part of the haystack, then we want to return -1. Now we want to do a third situation here, where if we're given a non-existent needle, i.e. needle's an empty string, we want to return 0 in that special case, as a way to say, no, that's silly, let's not do that. So, 3 different situations to handle. And example 1, 2, and 3 kind of goes over each of those situations, where you have something to find and you report the index because the first L that you want to see starts at index 0. This needle is not in this haystack, so -1, and we have a non-existent needle here, we output 0. Pretty straightforward. The constraints, haystack and needle, consist of only lowercase English characters. That's nice, so we don't have to worry about how to handle, say, things like spaces. And the constraints, we can have them being non-existent, 0, to fairly large. So this doesn't require too much code to technically handle. You could have an if statement at the beginning that checks to see if needle is empty, and if that's the case, then you return 0. One of the situations handled right then and there. Now, to search these haystacks and the needle and make sure a needle is present in a haystack, you're going to need some sort of nested loop present. The first loop can traverse the haystack, the second loop could traverse the needle, for instance. You're looking to see if the first characters in the haystack and the needle are the same. If they are, great. Continue doing the comparisons. If they aren't, you want to break out. Now, if you get to a situation where you've gone through the entire needle and you've found a matching subset of characters in the haystack that is a perfect match, hey, you found your needle, so if you've reached the end of the needle and you still have a match, you're still within that loop, then you can return your index. If you go through those nested loops completely and never have an opportunity to return the index, you never find a needle, then you can, at the end and outside of those loops, just return -1. Now those are the basic structures of this type of algorithm. Now we'll do that code, and then you'll see it will probably work, but it is highly unoptimized. But with just one tweak to it, we can make it take much less time. So let's move on to the code. First thing to do is the if check. So if the size of the needle is 0, we simply return 0. Next up is the nested for loops. So outer loop, beginning to the end of the haystack. Next up is an if statement that checks if the first character in the haystack matches the first character in the needle. If it does, then we go into a second for loop, from the beginning to the end of the needle this time. And similar if check here. If haystack I plus j is equal to needle j, then do an additional check here and see if you're at the end of the needle. If you're at the end of the needle, then you've gone through and found your needle in this haystack, and you can just return I. This condition here is a way to adjust the location of I by just iterating through j. Now, if this condition isn't true, in other words, we found a character mismatch somewhere, then we want to break out of this inner for loop and go back to the outer for loop to continue. The final thing to add is if you go through these loops and you never get the opportunity to go into this if statement here and return an index because you found a needle, well then you haven't found a needle and you just want to return -1. This code will probably work. And I say probably because, as you can see, this code is highly unoptimized. It will take a long time to run. But let's see if the servers are not being used quite so much and I can get it to pass. So this run code has finished and we get the expected answer. Now let's see if we submit the button, what happens. Okay, we get accepted. Now looking at quickly this time and space complexity, we aren't creating any additional variables besides I and j that's part of the loops that we're dealing with. So this will be a big O of 1 space complexity. For time complexity with nested loops here, everything else is just if statements and assignments. So the time complexity will depend on the number of iterations you're doing. And for this one, this for loop depends on haystack size, this for loop depends on needle size. So it's going to be a big O of, say, m times n, where m is haystack size, n is needle size. In other words, it takes a long time to do. And you can see that in the rankings here. And yeah. So here, this runtime has taken about 788 milliseconds. It's a long time. And I've seen this have some circumstances where it takes even longer here because of, say, server delays. And it could potentially take long enough that you don't even get it to pass. You could get a time limit exceeded because it's just so unoptimized. So we want to take this and get it up here somehow, where these higher bars are. Now, from memory, I've seen it ping pong around here. This distribution is indicative that if you're anywhere around here, you probably have a big O of 1 space complexity. But let's now go back to the problem and mess with it. First, before we do some tweaks, and you'll see it's a very minor tweak to dramatically speed up the process. But I want to show you first how to make it even worse. Let's comment out that if statement. So it has to go into the second loop, do these if else checks, and then figure out what to do instead of doing this if statement. Now let's see, it should still work for these small little test cases. But let's see what happens in the full submission. Judging, that's taking a really long time, you see, and we get a time limit exceeded. So this if statement does help reduce some checks, which reduces some time, and that allows this highly unoptimized code to be able to pass most of the time. So let's uncomment that out. Now, let's look at this time limit exceeded, where it's hard to see, but this is just like a really long string of A's here, and a really long string of A's plus a B at the end, as you see here. Now let's do this. Our haystack can just be a bunch of A's, and our needle can be a bunch of A's that is, say, 1 or 2 less, and the last A is substituted with a B. In this code here, with these nested loops, you're going through a haystack, you're starting at the beginning, and you want to see if you find a match. Well, considering these strings are almost exactly the same, except at the very end, you're going to get a match, and then you're going to start in the second loop and go through needle size. And you're going to go through all the way until the very end when you see a mismatch. And then you go through all of those checks, get to the end and see, oh, well, close but no cigar, we break out. Then you go back to the outer for loop, and you start in the second A, and the entire thing happens again. You have to search the entire needle again, get to the end, see you get a close but no cigar situation, break out of it, get to the third one, do it all again. You can see for very long strings, like say 5 times 10 to the 4th long, this is an issue. It takes a long time to work. However, if we have a super long string here, and essentially a super long string that's 1 less, by the time we get to, say, the third A here, the rest of the haystack size and the size of the needle are going to indicate that that needle is not going to possibly fit in the haystack. And that tells you the tweak that you need to do in order to make this run a lot faster. Instead of this outer loop going through the full haystack size, let's make it go through the haystack size minus, say, the needle size plus 1, because we're doing less than. If you're doing less than and equals, then you don't need this plus 1 here. This situation will mean, say, if we have 4 A's here and we have a needle that's 3 long, well, we can look at this first A, we get to the end of the needle, our hopes are dashed, and we go to the second one here. We still have 3 A's left in the size of the haystack to search, which equals the needle. So we could still possibly find it. Not in this situation, since again, when we move on to index equals 1 here and search through it, we still find at the end, we get a close but no cigar, but then we get to the third A, and by this time we only have 2 A's left in the haystack to look through. But our needle is 3 long. We can't possibly find it in the rest. So that means when we get to 4 minus 3, which would be 1, plus 1, 2, and we want to go less than that, so we're back to essentially index being 1. We go through this A, we go through this A, index 0, index 1, and as soon as index goes over to 2, we know we can't possibly find the needle again, so we break out of that loop and return -1. For long haystacks and long needles, that can dramatically speed up our search and eliminate those needless searches that happen in this situation here. Now, there's one additional issue here. When you're doing subtractions within the condition with here haystack size and needle size, it has an issue actually being able to do that before you go into it. I'll show you what I mean. We've made this change. Let's go ahead and run code. Pending, judging. It can work for this situation, but what about when the needle is much, much larger than the haystack? Say we have a custom test case here, and we want to look through A's, and we have a very, very, very long needle to search through. Well, you would think, okay, haystack size 4 minus, a much bigger needle here. You're going to have some deeply negative number even when you add +1 to it. And we try to evaluate the condition of, is 0 less than a negative number? Well, no, this condition is not true. We should skip the for loop entirely and just go directly to return -1. But look what happens. Pending, runtime error. Stack Overflow. And the reason for this is because it's not properly evaluating this condition here. However, you can fix that quite easily by essentially just making an integer variable and setting that to equal your string sizes. So we have integer m being equal to the haystack size, and we can have integer n here being equal to the needle size. In that case, we just substitute m right here and n right there, and then presto, this exact same test case, pending, more pending, judging, and now you can see it works because it's properly evaluating this condition here. And this condition automatically handles other weird things being given to you, like when the haystack is 0. So let's go ahead and just submit, pending, judging, accepted. Looking at space complexity and time complexity again, we have additional integer variables here, but those take up constant space, so our space complexity is still big O of 1. Looking at our time complexity, with this outer loop having a different condition here, it depends on both the haystack size and the needle size in an m minus n fashion. Then you have this inner loop here again. This is unchanged, it still depends on the needle size. So what you need to do is multiply those together. We have the m minus n dependency of the first for loop multiplied by the n dependency of the second for loop, and we get this. Our previous m times n dependency, but we have an additional factor here of n squared. Now between these two terms here, m times n is guaranteed to be bigger because the only way we're going to go into this for loop is if m is bigger than n. If it's not, the condition is not going to turn out to be true, and we're just going to skip it. So m times n is the bigger factor, but we're subtracting the n squared term, which is why the time complexity is so much better here. So looking at this, we're now going to see we've moved from down here to way up here where we want to be. We initially took around like 800 milliseconds. We're now 4 milliseconds. So that one tweak to the condition of the outer loop dramatically speeds up our algorithm. And we're still around the same area of memory usage. That was how to solve the implement strStr method problem on the LeetCode website. I hope you got something out of this video. If you did, consider subscribing. I do these types of videos twice a week. And as always, I will wish you happy coding and to have a nice day.